Widmanstatten ferrite. The formation of Widmanstatten ferrite is an example of displacive and civilian transformation. This is a typical TTT curve for a steel, which is a schematic, and this upper C curve represents a reconstructive transformation such as ferrite transformation. And below a typical temperature, which is designated MS, the transformation is displacive and multi-type of transformation known as martensite. There is a temperature which is represented here as the TH. This is the maximum temperature at which displacive type of transformations can take place. At a temperature near TH, the ferrite formation occurs by a displacive but civilian means, and the transformation product is known as the Widmanstatten ferrite. There are two ways by which the Widmanstatten ferrite can grow. So we have this, consequently we can differentiate as primary Widmanstatten ferrite and secondary Widmanstatten ferrite. The primary Widmanstatten ferrite is nucleated at the original austenite grain boundaries, and then the ferrite grows in the form of platelets. Which type of platelets? From the ferrite into the austenite grains. So this is called as the primary Widmanstatten ferrite. The secondary Widmanstatten ferrite is usually formed on the allotriomorphic ferrite, which is produced at the grain boundaries of austenite. So you have got, this is typically is the allotriomorphic ferrite, and then on top of that you have got the Widmanstatten ferrite, which type of platelets which are penetrating into the austenite grains. So these are called as the secondary Widmanstatten ferrites. The transformation is a displaced transformation which involves the diffusion of interstitial solute atoms. Because it is formed by the displaced transformation, there is a one-to-one correspondence of substitutional atoms of parent and the product phases. Carbon diffusion is essential. So the conditions under which the Widmanstatten ferrite forms can be designated as para-equilibrium. Widmanstatten ferrite can form at temperature close to AE3 than and hence can occur at very low driving forces. The undercooling needed amounts to a free energy change of only about 50 joules per mole. Because of this small undercoolings, the nucleation is relatively difficult. Hence a coarse microstructure is produced. The plates, which type of plates of Widmanstatten ferrite are coarse in nature. Inside the ferrite grains, no substructure is seen. Like other ferrites, Widmanstatten ferrite is white. In steels, the plates that nucleate at the aconite grain boundaries are designated primary, whereas others that develop from ferrite allotriomorphs are called as secondary. Widmanstatten ferrite plates have a lenticular edge with a overall shape replicating a thin wedge. This is a micrograph showing how the wedge type of plates are formed, and these are essentially Widmanstatten ferrites. So they are growing onto the essentially towards one side of the aconite boundary. Widmanstatten ferrite is structurally homogeneous. The mechanism of transformation is displacive, so that plates exhibit a reproducible combination of irrational habit plane and orientation relationship and shape deformation with parent aconite. There exists frequently low misorientation boundaries between plates of Widmanstatten ferrite. The plates of Widmanstatten ferrite taper to a fine edge in order to accommodate the elastic strain associated with the shape deformation accompanying the change in the crystal structure. So you can see very sharp tips of this Widmanstatten ferrite. Shape change. At low undercoolings at which Widmanstatten ferrite grows, the driving force is not sufficient to support the strain energy associated with a single plate. Widmanstatten ferrite formation therefore involves simultaneous and adjacent cooperative growth of two plates which are crystallographic variants, such that their shape deformations can mutually accommodate. A set of crystallographic plates and directions which belong to same indices define what is known as crystallographic variants. Thus, the formation of crystallographic variants simultaneously reduces much of the strain energy. This requirement of triggering the initiation of two plates simultaneously makes the nucleation relatively difficult. So you have got this is one plate which is formed by means of a displacer mechanism, and this is another plate. So consequently, the strain strain component which is produced by this plate is alleviated by the formation of this plate. So the deformation was the formation of invariant plane strain deformation. And a single plate is seen in the optical microscope is usually a combination of two variants. So this is clearly an example of what a crystallographic variant means. So this particular plate has got a planar orientation. That means the plate is parallel to a crystallographic plane 558 of austenite. The associated adjacent plate, which is alpha W2 here, has got a crystallographic orientation of 585 of austenite. So if H, K, L are the indices, and by varying the positions of H, K, L, we can all the planes, crystallographic planes which are created, they are said to belong to the same family. And here by the position of heat which is there here in the last index is becoming middle one, so consequently this and this are said to belong to same crystallographic family of planes. And one plane of Widmanstatten ferrite has got this index, then other plane has got this index, which both of them belong to this same crystallographic family of planes. So consequently these two are called as the crystallographic variants. A single plate as seen in the optical microscope is actually a combination of two variants, usually separated by a low angle boundary. So this is the dashed line is a low angle boundary. Widmanstatten ferrite has a habit plane which is close to 558 of the austenite. Hence the two plates alpha W1 and alpha W2 which have the different variants of this habit plane with the austenite together form a thin wedge shaped plate which is characteristic of Widmanstatten ferrite. So the requirement here is to accommodate the involved strains, so consequently reduce the overall strain energy. The Widmanstatten ferrite transformation can be mechanically stabilized. This is again a characteristic of displacive transformation. Not only is the plate-like microstructure of Widmanstatten ferrite is refined and disrupted when it grows in a deformed austenite, but the total quantity obtained during isothermal transformation is also reduced because the extent of transformation per nucleus is also reduced. Microstructures containing Widmanstatten ferrite are weak and possess inferior strength and are brittle. So, apart from the academic interest, particularly of displacive transformations, the microstructures of Widmanstatten ferrite are not suitable for practical applications because of the brittleness this particular transformation imposes to the mechanical properties of the steel.